everyone, and welcome to our lecture video introducing and talking about the ideal gas law. By the end of this lecture video, you will be able to put together the relationship of the four variables we talked about and articulate them in the ideal gas law, and also be able to articulate the behavior of ideal gases. So, you may have seen the ideal gas law before. I'm sure maybe you've seen this in a previous PCB class, but even if it's been a while, we're going to go ahead and review from the beginning. But first, I really want to reiterate, so far in our basic gas laws, it didn't necessarily matter what units of pressure, what units of temperature you plugged in, what units of volume you plugged in, as long as they were consistent. But from here on out, especially in our ideal gas law, you have to use very specific units when you plug into the equation. So when you plug in pressure from here on out, you have to plug in atmospheres. When you plug in volume, you have to plug in liters. When you plug in moles, the only option is moles. And for temperature, you have to plug in Kelvin. As a reminder, our unit conversion between Celsius and Kelvin are here. To have your temperature in Kelvin, you need to have the temperature in degrees Celsius plus 273.15. So to introduce the ideal gas law, this is one of the most famous equations in all of chemistry. And while you're given this on the equation sheet, so you don't explicitly have to memorize it, you can also interpret all the other gas laws from this specific equation that I'll show you in just a moment. But the ideal gas law is PV-NERT. PV, so pressure times volume, is equal to NERT, number of moles, times R, which is your ideal gas constant, times temperature. Notice the R value that we use, this ideal gas constant, and as always, you're given constants on your equation sheet, so you don't need to remember this, but let's look at our units. The units for our ideal gas constant are liters times atmospheres divided by moles times Kelvin. That is why when I plug in my pressure, my moles, my temperature, and my volume, I have to use very specific units because my constant has very specific units. So PV-NERT is our ideal gas law, but embedded into this is already the proportionality and inverse proportionality that we explored in our basic gas laws. So if I take PV-NERT, right, but I say, let's hold number of moles and temperature constant, right? That means that my number of moles, N, my R is a constant, so it's always constant, and my temperature is also constant. So if I look at the relationship between volume and pressure, I notice that volume is equal to 1 over pressure, or it's inversely proportional. That's Boyle's law that we already explored in our last class. Next, if I hold number of moles and pressure constant, the red variables here, N, R, and P are all constant, which means V is directly proportional with temperature, which is Charles' law. That's what we talked about last time. We said that as we increase our temperature, I'm increasing my volume of my gas as well. And last but not least, if I keep my pressure and temperature constant, we see Avogadro's law in action. We see that as I increase my number of moles of N, I'm also going to increase my volume. So PV-NERT already embeds into it this type of relationship that we already explored in terms of gas laws. So oftentimes what we're going to see is a whole bunch of practice problems, but PV-NERT is going to be a theme through the rest of our unit, and we're going to see it in a lab next week. We're going to see it embedded into our Unit 3 throughout the rest of the next couple of weeks. So let's talk through a practice problem. We're asked how many grams of gas are present in the following cases. I have 0.10 liters of CO2 at 307 torr and 26 degrees Celsius. This is a pretty straight up problem. I'm just giving you everything right away. But what I would recommend doing is writing out your givens. We have our volume, we have our pressure, and we have our temperature. For me, what we need to know is that I'm trying to find my grams of gas. Using any equation that we have so far for our gas laws, I can't find grams directly. I'm going to have to solve for moles first. So I know I have to use my PV-NERT equation, but here I know that I can't plug in torr and I can't plug in degrees Celsius. So I have to convert those to atmospheres for pressure and my Kelvin for temperature. And because I can't find grams directly, we have to find moles or N first. So when I solve for N is equal to PV divided by RT. And now it's just a game of plug and chug. We have our pressure times our volume divided by our constant times our temperature. And when I plug that into my calculator, we get that we have 0.00165 moles of carbon dioxide produced. But that's not what I want. I want grams of CO2 that are present. So we have to use our molar mass and know that the molar mass of CO2 is 44.01 grams per mole. So I use that as my conversion factor and multiply my grams into my moles. And we end up getting that this specific volume, pressure, temperature is corresponding to 0.0726 grams of CO2. So for part of homework today, you're going to continue to do some more practice problems. So feel free to come back to this video if you need some guidance while doing that. But before wrapping up, I wanted to introduce two last things. Oftentimes when we're talking about gases, we can refer to a set of conditions called standard temperature and pressure, or STP. Standard pressure tells us that our conditions of pressure are 1 atmospheres, and my standard temperature tells me that my temperature conditions are 0 degrees Celsius or 273.15 Kelvin. So sometimes you might see problems that say this experiment was run at STP. You then have to be able to understand that that means standard temperature and pressure, and use your standard pressure and use your standard temperature. These values are given on your equation sheet, so you can always refer to the equation sheet then, but you still have to be able to know what STP is in order to be able to apply it. The last concept that I wanted to talk about is this idea of the molar volume of a gas. And if you look ahead into next week, we are doing a lab to quantify the molar volume of hydrogen gas specifically. So we're going to do an experiment to verify and check our number. But what this is, the word molar, right, tells me for 1 mole. It's saying for 1 mole, what is the volume of my gas, specifically at STP. So the molar volume of a gas is derived from the ideal gas law, and it's saying if I have exactly 1 mole of a gas at STP, it will always occupy 1 volume. So my volume is equal to nRT over P because I've isolated my volume variable and solved using Pivnert. I plug in, we have 1 mole of our gas, we have our gas constant. STP means that we have 273 Kelvin and 1 atmosphere, and the volume that I get is 22.42 liters. What that means is if I have 1 mole of any gas at all, if I have 1 mole of that gas at STP, and we assume it's an ideal gas, that means that 1 mole of any type of gas will always occupy 22.42 liters. We are going to investigate this further in our lab next week, so stay tuned for that. And now go on to our last lecture video before practicing some homework worksheet problems. Bye, everyone.